Hello and welcome everyone to our channel Intromech. In last two videos we have seen some basics about the stress and types of stresses, then different types of loadings. Now in this lecture we will see the strain and some other concepts. So when I say strain, strain is nothing but the deformation, or we can say the elemental deformation of a body under the application of load. So let's consider here a body which is subjected to the normal force P. Okay, so if I consider this part as split into different elements, so this body is made up of elements. So when the force P is applied, this body gets elongated in this direction. Okay, each element gets stretched into this direction, and because of which the total body gets elongated by, let's say, by delta L. Okay, so this is the increase in the length of the body, and the initial length of the body is L. Okay, so strain, or here we can say as a normal strain, because it is the strain because of the normal force P. So it is nothing but the change in dimension upon original dimension. Okay, so what is here change in the dimension, that is delta L, and what is the original dimension L. Now change in length will be in mm. Okay, and the original length is also in mm. So strain will not have any units. Okay, so it is nothing but the total deformation per unit original length. Okay, so next is the most important part, that is the strain curve. So here we have drawn the stress strain curve for the mild steel, or we can say a low carbon steel. Okay, so this is the curve which we obtain when we apply the specimen on the universal testing machine, and when we pull that job under the load, then we get this curve. Now in this curve we can say A. So this point A is called as limit of proportionality. So what does it mean? It means that from this point to this point, the stress is directly proportional to strain. That means sigma is directly proportional to strain up to this point. That is the limit of proportionality. And if we see, if I say this sigma is proportional to E, if we remove this proportionality sign, then we can write as sigma is nothing but E into E. This E is nothing but the Young's modulus of elasticity, which is the property of material, and this is denoted by E. So this is also called as a Hooke's law. So what is it, does it tell? That within the limit of proportionality, the stress is directly proportional to strain. Okay, so this, if we observe, then this is nothing but the slope of this curve. So E is nothing but the slope of this curve. Okay, so if we move forward, then this is the point B. So this point B is called as elastic limit. So it is elastic limit of the material. Now what does it mean? It means that the material is elastic up to point B. That means it can regain its original shape up to point B. But the basic difference between point A and B is that you can see there is a slight curvature here. What does it mean? It means that stress is not directly proportional to strain in this region. Stress is directly proportional to strain only up to the limit of proportionality. It is strictly proportional up to the limit of proportionality only. So this point is very important, and most of the time people gets confused between limit of proportionality and elastic limit. So stress is directly proportional to strain only up to limit of proportionality only. Okay, so after that this point C is called as upper yield point, and this point generally we do not consider from the design point of view because it is not particular, and after that there is a sudden drop of the stress value, and this point is called as lower yield point, which is considered for the designing of the material. And if you see now this curve, we can observe that strain is increasing without much application of the load. That means the material is getting stretched, or from metallurgical point of view we can say that there is a slip phenomenon between the molecules, because of which it is getting stretched. So in this region there is no elastic recovery of the material, so we can observe the strain is increasing. So this is called as plastic zone. This was the elastic zone because material was regaining its original shape and size. Here it is a plastic zone because material is not able to regain its original shape. It has undergone into the plastic zone. Okay, so after E point, this G point is called as, so C was our upper yield point, then D was our lower yield point, okay, then G is ultimate stress. Okay, so the stress which corresponds to point G, it is called as ultimate stress. Now in this region the material gets strain hardened, so it is called as strain hardening zone. The material requires more force to get stretched, and because of this we have a ultimate stress point. Okay, so after ultimate stress point there is necking. That means the material start getting weakened. So if initial our bar is like this, okay, so after G point there is a neck formation in the material, so cross section area start reducing and material gets fractured at this point. So F is fracture or necking point, and this zone is called as a necking zone. So the stress which is corresponding to point G is our sigma ut, the ultimate stress, and then this is our sigma yt yield point stress. Okay, so this curve is very important, and the zones are also very important. Now if you observe, I have drawn another curve which is like this. So it is not following this curve, but it is like straight away. This is going like this. Now what it is? Now the curve which we have drawn here, this curve, it is our engineering curve. Or engineering curve, and this is our true stress curve. Okay, now this is also very important and interesting. What is the difference between these two stress curve and engineering curve? Okay, so if we see here, when I say stress, it is force upon area. Now it is important that this area which we are considering is what? Now here we can see that under loading the cross-sectional area of the material is getting reduced, okay, as the time passes. So area is reducing, but for the engineering curve we consider this area as original area or nominal area. So we consider this area for each sections. So even if at this section area has reduced, we are considering this original area AO for this curve. Okay, so In this case, if we see here, the force is getting reducing, okay, but the area is constant, which is AO. Okay, so area is original, but the force is reducing. That's why here stress is reducing. On the other hand, that means the engineering stress is nothing but the force upon original area, or it is also called as nominal area. Okay, and on the other hand, if we consider this true stress curve, then in this true stress we are considering the area at each time interval. So we are considering the actual reduction in area at each time interval. Okay, so that's why we can see here the area has reduced, so that's why here stress is getting continuously increasing. There is no drop of the stress value, because here we have considered the original area, and here we are considering the actual area. So AC is nothing but our actual area at that particular time interval. Okay, so this is the basic difference between true stress curve and engineering curve. So if it is asked, or now it is definitely clear that the true stress and the engineering stress values are not same. They are different values. So what is the relation? So if we consider sigma t as a true stress, then it will be equal to sigma into 1 plus E. So sigma is the engineering stress and E is the engineering strain. So, likewise, if I want to calculate the true strain, which is denoted by epsilon, it is log of 1 plus E. So this is the relation between the true stress and engineering stress and true strain and engineering strain. Now, the curve which we discussed earlier was for low carbon steel or mild steel. So it has, if we see here, it has upper and lower yield point. Okay, so for all material, the upper and lower points are not significant. So there is not a much difference, or we cannot differentiate between the upper and lower yield points. So if we consider the high carbon steel or the brittle materials, here we can see there is the elastic limit, then the ultimate strength, and there is a breaking. So this is the ideal elastoplastic material curve. Okay, and this is the ideal plastic material curve, and this is ideal rigid material curve. There is no strain, so this is the rigid material. Okay, next part is, okay, now if I consider the same material and I am applying different forces and I have taken different cross-sectional areas, so I will get different curves of load versus deformation. Now here P is the load and delta is the deformation. Okay, so here you can clearly see that these curves are so many. For the same material, this curve can be different at different loads and different cross-sectional area. So this is not the property of material, but on the same hand, if you consider the stress-strain curve, then this will be unique for the material. So this is the property of material, because a single material will have a same stress-strain curve. Okay, so it will not vary according to the load or cross-sectional area. So this is the basic difference between this load versus deformation and stress versus strain diagram. Okay, now next is, so here we have considered a round bar and it is subjected to the normal force. Let's consider P. So we have seen that the normal strain is nothing but the change in the dimension upon original dimension. So here let's consider L is the original length of the bar, then this is the change in length after application of load, then this is the original dia D, and this is the change in diameter after elongation delta D. So here the strain, there are two terms, that is the linear strain, okay, and then the lateral strain. Now, what is linear strain? The linear strain is the strain generated in the dimension which is in the direction of application of load. So here length is along the direction of load P, so your linear strain will be change in length upon original length. And what is the lateral strain? The strain which is getting generated in the direction perpendicular to the direction of loading. So here dia will get reduced as the length is getting increased. Okay, so what is the lateral strain? It is delta D by D, and as you can observe here, it is getting reduced, it is compressing. So this will be minus as the dimension is getting reduced. Now what is Poisson's ratio? It is denoted by mu, and it is minus lateral strain upon linear strain. Okay, so it is lateral strain upon linear strain. So this is nothing but minus, here we have lateral strain as delta D by D and linear strain is delta L by L. So this minus minus will get cancelled and we will have positive Poisson's ratio. Okay, that means for the materials in which this dimension is reduced as one dimension is getting increased, so for those materials this value will be positive. Now for some materials this value can be positive, that means on the application of this load the other dimension is getting enlarged. So for those materials this lateral strain will also be positive and this linear strain will also be positive, so the Poisson's ratio will be negative. And for some materials the Poisson's ratio is 0. What does it mean? For those materials the lateral strain is 0, because of which the mu is 0. So the Poisson's ratio can be positive, can be negative or 0. The general materials if we consider, then the cork material has almost equal to 0 Poisson's ratio, then concrete has nearly 0.2, then the steel according to the grade will varies between 0.25 to 0.33, and rubber is having the Poisson's ratio of 0.5. What is the physical significance of this Poisson's ratio? It is very important. Now let's consider a practical example of a pipe carrying fluid. Now I am considering two pipes which are joined together, okay, and the fluid is flowing inside this pipe. Okay, now we know that the fluid exerts equal pressure in all directions, Pascal's law. Okay, so it is applying the force pressure in all the direction, because of which the hoop stress is getting generated. That means the stress tries to increase the pipe diameter, okay, and because of which the length try to get reduced, and because of this what happens, this is the joint. Okay, so this joint can fail if this strain is higher, that means the compression of these pipes is higher, then this pipe can fail at the joint. So it is very important to consider this. Okay, now second example, if we consider this cork. Okay, so if we consider the cork, it has almost 0 Poisson's ratio. So if we consider some bottles, and for those bottles the upper cap is it is joined with the cork piece. Okay, So what is the advantage of this cork is when we insert it, it doesn't get elongated and we can easily apply the cork inside the bottle. The only cause is the friction between this cork and this bottle material, and because of which it becomes sealed. So we don't have to apply much force because it is not getting elongated. Similarly, if we, on the contrary, if we consider some hoses, okay, now some pipe is there and some hose is there, okay, and if you are trying to pull this hose, then what will happen? It is trying to elongate in this direction and it is trying to compress in this direction, so it is difficult to remove this pipe. Okay, so this is another physical significance of the Poisson's ratio. And I think this is so the last one, which is nothing but which we have already seen, the Young's modulus. Okay, then the shear modulus, which is also called as modulus of rigidity, and then the bulk modulus. So as we have seen, the Young's modulus, that is the stress, that is the normal stress is proportional to normal strain with its elastic limit. Similarly, for the shear modulus, the shear stress is proportional to, let's say, shear strain, and for the bulk modulus, there is a change in volume and on the application of pressure. So there is a relation between these terms and Poisson's ratio. So E is 2 times G into 1 plus mu. Then again E can be written as 3 times K into 1 minus 2 mu, and E is equal to 9 times Kg upon 3K plus G. So with these interrelations we can find out the different values for a material, and all these properties are material properties. So for steel, this E, G and K will be some particular value. For copper will be fixed value, then for brass that will be a fixed value. So these are material properties. So thank you guys for the patient listening, and we have covered almost the basic concepts in the mechanical engineering, and I hope you understood the things. And if you have any doubts, please do write in the comment section. Until then, be safe and stay happy. Thank you.